Hello there. Today we're going to look at efficient and modular implicit differentiation by researchers of Google Research. This paper on a high level extends what you know from frameworks like TensorFlow or PyTorch or JAX in terms of automatic differentiation. It extends it to multi-level optimization procedures. So this paper makes it possible that you differentiate through an inner optimization loop without having to unroll that inner optimization loop and without having to implement the optimization procedure in a differentiable way. This has been done before for single instances of problems, always with sort of specific derivations for that particular problem. But this paper provides a unified framework of doing this. And so it's a bit of a technical paper, and we won't go in this too technical mode because I'm also not the most or the biggest expert on the methods used here. I just wanted to raise a bit of awareness that this exists, because the ability to backpropagate through sort of inner optimization procedures and even like other things in a unified way without having to unroll, I think it unlocks a bunch of research that has been quite cumbersome so far and could be interesting to a lot of people. They do provide code and everything, and they prove, or they show, that many special instances that have been derived in the past, and also a bunch of new ones, are just instances of their framework and can be solved sometimes much more easily with their framework. They even provide some approximation guarantees and so on. I think interesting to us is just going to be a little bit of the insight of why and how this works and the fact that it exists. So let's jump in. They say that automatic differentiation has revolutionized machine learning. It allows expressing complex computations by composing elementary ones in creative ways and removes the burden of computing their derivatives by hand. This is absolutely true. If you look at old papers in deep learning, half the paper would be spent on deriving the gradients of the architecture that was just proposed so you could actually implement it. And now we have AutoDiff, which means that the frameworks, they simply do this by themselves. You just compose a bunch of functions and you call gradient on them. This is a big part of what has spurred the deep learning revolution in the past few years, at least from a implementation point of view, right? I don't think a lot of architectures would have happened if people always had to derive the gradients by hand. And it's kind of obvious to do this if you know the backprop algorithm, but still it is a big helper. Now, as I said, this paper extends the concept, the spirit of AutoDiff to a much larger class of applications. They say more recently, differentiation of optimization problem solutions has attracted widespread attention, with applications such as optimization as a layer and in bi-level problems such as hyperparameter optimization and meta-learning. So the key here is differentiation of optimization problem solutions. So I have an inner optimization problem and I obtain a solution, and I want to backpropagate through, not only through the solution itself, but actually through the path that led me to finding that solution. And meta-learning is a good example, hyperparameter optimization, of course, as well. So in meta-learning, what you do, and this is a simple thing. There are many various tasks in meta-learning, but I've done a video on one of those, which is called iMaml. It's an extension of MAML, and I think the ML stands for meta-learning. The I here for implicit, which is of course going to be related to the implicit differentiation we do right here, or implicit. The implicit here stands for the fact that we can implicitly derive the gradient. We don't have to go through the whole unrolling. So in iMaml, there is a setting where you have multiple tasks. You have a data set, and there is task 1, task 2, and task 3. So maybe This is classifying food by taste. This is classifying food by calories. This is classifying food by some other nutrient or color or something like this. And this all should happen with the same architecture of neural network, simply solving different tasks. So obviously the different tasks are going to have different optima, different local optima. And from deep learning, of course, we know that these are never in the same place. There are many local optima, but let's just pretend for a moment we knew that these were the 3 optima. The task of meta-learning is, can we find an initialization that is really good, such that if we fine-tune on any of these tasks, if we get data from any of these tasks, we can learn it really quickly. So if if you see here, if we choose this as an initialization, it's going to take us a while to get to any of these solutions. However, if we choose this as our initialization, we're here pretty quickly. And in fact, if a new task comes that is similar to the other ones, let's say one here, right? That's kind of similar. It's on the same hyperplane, whatnot. You can see that we're also there fairly quickly. So the question is, how do we find the blue point? Obviously, we don't know where the green points are, and they're non-deterministic anyway. And the answer is, we start with any one, like this one. We start with a guess, and we move step by step into a better direction, just as we do with gradient descent. However, how do we know what a good direction is? In order to know what a good direction is, we need to know how good is this initialization. So consider this one. How good is this initialization? Well, in order to do that, we actually need to do the optimization procedure. So we do that, and we see, well, that leads us in that direction. We optimize for a different task, that leads us in that direction. And now we get an idea that, hey, maybe if all the tasks go into the same direction, maybe, it would be good if we also went into that direction. Specifically, what we want is, we want the gradient. The gradient with respect to our initialization of the solution of a particular task given that initialization, right? Now, this solution itself, of course, is an optimization procedure. So you have an inner optimization procedure that you want to backpropagate through. What you usually have to do is you have to unroll that optimization procedure. So if you think of gradient descent, so here is your weights, and what you do is you subtract learning rate times the gradient. So here is it at step T, right? Learning rate with respect to the weights of f of x and wt. Okay, that's your standard gradient descent. So what does that give you? All of that gives you wt plus 1. And now you do another step of gradient descent. Okay, so minus, again, gradient with respect to this. Maybe it's a different data point, maybe it's the same, plus 1. Okay, so it already gets complicated, because now this quantity here, which is all the quantity of above, appears twice. Okay, and if you do another step, of course, that quantity is going to replicate and be anywhere. An autodiff framework can keep track of that. So if you do this and you actually write down from your first thing, you write down, you can unroll all of this into one big expression that gives you the end of the optimization procedure, the end of gradient descent, given the beginning. You can do that. And the TensorFlow or PyTorch, they can keep track of this. It's going to be a big expression. It's going to be really, really slow. And further, what you need to do is you need to actually implement the gradient descent procedure as a differentiable procedure, which is usually not done. Usually, especially in TensorFlow and PyTorch, the gradient descent, the optimization procedures, they're sort of outside of the autodiff framework. In JAX, it's a bit different, but in TensorFlow and PyTorch, the optimization procedures, for good reason, they themselves aren't differentiable, so you'd have to re-implement them in a differentiable way. All of that is fairly cumbersome. And people have asked themselves, can we do better? Especially in this technique called IMAML, people have found that instead of unrolling, what we can do is, if we regularize this objective in sort of a good way, so we add some sort of a regularizer here, then we can calculate the gradient, this outer gradient, without having to go through the whole unrolling step. A similar situation you can imagine with hyperparameter optimization. If you actually want to do gradient descent on your hyperparameter, so you have some sort of a validation set, right? You want to minimize your loss on your validation set, right? Of your with respect to your hyperparameter lambda, okay? And the solution you find is you minimize with respect to the weights of your loss function on the training set. This is all green and looks horrible, but okay, I think that's it. Okay, so you want to, we need a lambda. We need a lambda right here. Okay, so for a given lambda, for a given hyperparameter, we want to find the best weights, okay? But then we want to find the best lambda such that the weights give us the best validation loss, right? Such that the weights that came from the training data set give us the best validation loss. We do this right now with grid search, but we could definitely imagine doing this with gradient descent if we could get a gradient for that hyperparameter. But that requires us to backpropagate through this inner optimization procedure, through the actual learning of the neural network. Now, given that neural networks usually train in thousands or millions of steps, unrolling that is not going to be an option. Like, TensorFlow is good, but it's not that good. Okay, so it can technically keep track of it, but it's just not going to be possible. So for all of these problems, or for many of these problems, people have devised individual solutions. Like, given very, very strict requirements, given the exact problem formulations, we do have solutions where we don't have to unroll. However, these are case by case, and much like the old papers on neural networks, where every time you have to derive your gradient, here every one of these papers has to sort of derive how they apply their conditions, how they apply the Karush-Kuhn-Tucker conditions in order to get the implicit gradient and so on. And this paper is what AutoDiff is for these old papers. So they go on. Yeah, they say it involves case-by-case tedious mathematical derivations. In this paper, we propose a unified, efficient, and modular approach for implicit differentiation of optimization problems. In our approach, the user defines, in Python in the case of our implementation, a function f capturing the optimality conditions of the problem to be differentiated. Once this is done, we leverage AutoDiff on f and implicit differentiation to automatically differentiate the optimization problem. Okay, so what you do is you don't specify the gradient of the optimization procedure. You specify a function that captures the optimality conditions of the problem to be differentiated. And if that function here is differentiable, then this framework can do its magic to give you the gradient through the optimization procedure. So we shift away from the optimization procedure itself having to be differentiable to only the specification of the optimality conditions having to be differentiable, which is a huge gain, right? Yeah, so they say this can be actually done in many ways. You can choose your solver and so on, but we'll go through the very, very basics right here. Okay, this is ultimately what is going to end up, and this is a problem of, I think, hyperparameter optimization, as we saw. So this is ridge regression, and ridge regression is you have a data set, okay? You have labels. So X is a matrix where each kind of row I think, is or column, I think row, as a data point, and y is a vector of labels, numeric labels. And what you want to do is you want to find weights, w, such that w times x equals to y. Okay. That is linear regression, of course. Now, in ridge regression, you have a regularization on on w. So it's easier often to specify the loss. So what you want is that this is small, but also that w has some small norm. And so you want this being small, and you want the norm of w also to be small. And this is a common regularization technique to want the norm of w to be small. It sort of means that your line kind of stays rather flat. So if you have a bunch of outliers, they won't affect your approximation too much. It's a very common technique. The important part is there is a hyperparameter right here, and this hyperparameter is a matter of choice. This is the regularization constant. Now, with this framework, we can run gradient descent on that hyperparameter. And the way we do it is the following. So we start actually with down here. So this called ridge solver. This is the inner optimization. This is the solver of the ridge regression. Now, ridge regression has a closed form solution. We can just solve, we can put this as a linear problem. So here you get x times x, and here you get x times y, and then you get yourself a diagonal matrix that you can multiply with the regularization constant, and then you can simply put up this linear system. So that's the linear system corresponds to x times x plus theta. Well, in this case, in our case, it was lambda. This should equal to x times y. So if you solve this, then you'll get, if you solve this, you'll get the, what am I saying? Sorry, the linear system is going to be this times w. If you solve this for w, you'll get the direct solution to ridge regression. There's no gradient descent here, but it would be totally cool if this contained gradient descent. Okay, the next thing you'd have to do is you have to specify the optimality conditions. Now, in this case, we're sort of going to repeat the loss function of ridge regression. So as you can see here, the optimality conditions, of course, are dependent on x here, and x is going to be the w, actually, what we call w. And theta is your hyperparameter. So you can see this is just the loss here. You multiply w by x and subtract y. That's what's called the residual. And this here is the square norm of that. So in our loss function up here, we'd have sort of square L2 norms everywhere. And you can see here, this is the regularization. And the half here is for easier differentiation. We don't have it, but doesn't matter. Okay, so this here is simply the loss function of ridge regression. You can imagine more complicated things. Now, if I give you the loss function, what you need to give me is a function that is 0 when optimality is met. And now that's pretty easy. If I have a loss function, the gradient of that loss function is exactly such a function. Okay, the gradient of the loss function is 0 whenever the inner problem is optimal. So whenever the ridge regression is solved to optimality, the gradient of this loss function is 0. Now we have all the ingredients. So what we can do now is we can use their custom decorator right here to say that here is the optimality condition. F is the optimality condition on this inner optimization problem. And if you do this, then you can just backpropagate through that. So here you can see that you can take the Jacobian of the ridge solver at here, this is lambda equals 10, for example. So you can simply take derivatives through the inner optimization procedure because you have supplied this without having to backpropagate through the inner procedure itself. I hope this was a little bit clear. So again, you need to specify, of course, the inner procedure, which is this thing here. In our meta-learning case, this would be the gradient descent, the inner gradient descent. You need to specify the optimality conditions, which in the easy case is simply a loss function, and then the optimality condition is the derivative or the gradient of the loss function. It's optimal whenever that is 0. Then you supply the optimality condition in the custom annotation to the function, and then you can simply treat that inner function as if it were any other thing that you could backpropagate through. So cool, so cool. Okay, they go into the whole math behind this, and I don't want to go too much into the math, but all of this essentially comes from the implicit function theorem. So if you have this optimality condition, you may have noticed it needs to be 0 at optimum, and this is what's called a root, and the root is specified like this. So you have this inner function that depends on theta, and you have the optimality condition that depends on the solution to the inner function, and it depends on or can depend on the parameter itself. If you have a construct like this, under some regularity conditions on f, the implicit function theorem tells you that in essence you can express the gradient of these things with respect to each other. So from this you can get the derivative of this inner thing. You can get that locally, okay, without having to backpropagate through the procedure of how you found it. So, right? So it's an implicit gradient because it's defined as implicitly as a function of the other argument right here. If you look at this thing and you take the total derivative of this right here, you can use the chain rule to arrive at the expression down here. So if you derive the first argument right here, you get the chain rule in theta, right? So you differentiate with respect to the first argument, and then you also have to differentiate that first argument right here. And then you differentiate with respect to the second argument, and that is already theta, of course. So now you can see we've ended up with only partial derivatives right here of simple arguments. So we need 3 things ultimately. You see, this is the thing we want, the gradient of the solution of the inner optimization procedure. Now, if we reorder a bit, you can see the other things that we need for that is the number 0. That's easy. We need 2 derivatives of f. Both are just simple partial derivatives with respect to the arguments of f. And if f, therefore, is differentiable, then we can get those things, right? And that's the exact shift I talked about before. So instead of the optimization procedure having to be differentiable, only the optimality condition now needs to be differentiable. And that's a much easier thing. And again, we can use autodiff. We can use these frameworks for that. So as long as we can specify f in terms of somehow functions of the framework, we're good. So obviously this function here is fully differentiable because it's the loss of logistic regression. The only tricky thing right here is that big F, capital F, is actually the gradient of that function. So what we need is the framework to be able to differentiate the gradient again. So to obviously the gradient of, or the derivative of capital F would be the derivative of lowercase f. But usually frameworks can do this, right? And this loss function is certainly differentiable twice. All right, and then it's just a linear system, as you can see down here. So this this is what they call A, this is B, this is J. So what you have to do is you solve the linear system AX equals B, and then whatever comes out here, that's your gradient. And you can use any classic sort of linear solver for that. So to repeat, you obtain A and B by using autodiff on the optimality conditions, and then you simply have to solve a linear system to get the gradient of your solution of the inner optimization problem without ever having to unroll that inner optimization procedure, without having to backpropagate through the steps of how you arrived at that inner optimum. And that's the cool trick right here. So they can't only do this with a root, they can also do this with optimalities that are specified as fixed points. So whenever the optimal solution to the inner problem has the property of being a fixed point of some function t, can also use this method. So I think they provide two different decorators. One is custom root and one is a custom fixed point. And from there you go. So they discuss what they need. They discuss the technicalities. They actually don't ever need to calculate these things fully because they could become pretty big. They actually only need to calculate Jacobian vector products and vector Jacobian products, and they go into the technicalities here of how they obtain those. And the cool thing is that this fully integrates with the autodiff framework. So here they talk about pre-processing and post-processing mappings. So, what if we don't need the solution of the inner problem itself? What if we need a function of that, and so on? This can all be taken care of by the autodiff framework itself. So they see our implementation is based on JAX, and they say it enters the picture in at least two ways. We can lean heavily on JAX within our implementation, and we integrate the differentiation routines introduced by our framework into JAX's existing autodiff system. In doing the latter, we override JAX's default autodiff behavior, e.g. of differentiating transparently through an iterative solver's unrolled iterations. So if you stick this in, you can just differentiate through these things as if they were any other differentiable function in JAX. Very, very cool. So the last thing, so here are all the different things that reduce to their method. If you actually, if you go and look, they give a lot of different examples of what other techniques reduce to their methods. Specifically, we've seen these simple optimization procedures, but you can also do sort of proximal methods in the inner optimization problem. You can do things like projected gradient fixed point, which is maybe important for something like adversarial examples, where you have to minimize a function, but at the same time you have to stay within some convex set, so you always back project onto that set. So now we can back propagate through the procedure of finding an adversarial example. Very cool. And they even give bounds, because you cannot ever exactly calculate these things, so they give bounds on how far you're off. And lastly, they do experiments, and these are just more examples. So their first experiment, pretty straightforward, hyperparameter optimization of multi-class SVMs. So in a support vector machine, you generally have a hyperparameter, and that hyperparameter here is sort of the strength of the regularization, or like how much you trade off margin versus slack, I believe. I haven't done SVMs in a long time, especially multi-class. Yet you need to stay within. You need to maximize the margin while staying within the probability simplex, because it's multi-class. So that's kind of a constrained inner problem. But you would like to find the best hyperparameter for the trade-off parameter for the SVM with respect to an outer validation set. Okay, so that's a a problem with 2 levels, and they can do it right here. They can do dictionary learning. So usually in dictionary learning, it's not, you need to somehow obtain the dictionary and then you optimize using the dictionary. So in dictionary learning, you have some sort of a data point, maybe an image, and you map that into entries in a dictionary. And then you use those entries to do something with it, and then you have some kind of a loss right here. However, you can't optimize these functions that map and the dictionary itself at the same time. It becomes unstable. So what people do is they do alternating, or they backpropagate through some inner thing. You know, in this thing, you can actually backpropagate through the inner thing, through the inner problem, and find those dictionary elements as a function of which dictionary elements would actually most optimally solve the outer problems. Lastly, this is dataset distillation. They want to find the optimal dataset of size 10, right? This is the dataset. Give me one image per class, and if I train a neural network or whatever on that class, on that dataset of 10 images, I want the best possible validation loss, okay? And that is an optimization problem. So what you need to do is you need to start with 10 random images. You train your classifier, you measure it on the validation set or whatever, the test set, and then you backpropagate through the whole thing to update your data set itself. And in the end, you end up with the optimal data set. You can see that this is also a 2-level optimization problem with maybe some constraints right here. I think this is a very cool idea, honestly. It's probably, it existed before, but you can now do this. And in last, they have these molecular dynamics where they want to see if we change kind of the size of these molecules, how do all of these things change, so on. Again, this reduces to quite complex. This is the inner problem right here. But I think the point of all of this is that if you have a problem where it has sort of an outer and inner optimization structure, and you want to use backpropagation for the outer problem through the inner problem, give this method a try. It's pretty cool. If you're interested in the more technical aspect, give it a read. And that was it from me. I wish you a pleasant rest of the day. Bye-bye.